In this video, we're going to go over energy conservation in simple harmonic motion. Now, this is one of the subunits of simple harmonic motion, but if you have already mastered energy conservation unit, this video that we watched before, then this should be a really easy unit for you. So in the first few minutes, we'll discuss how does energy conservation apply to simple harmonic oscillators. And for the rest of the video, we'll solve 3 practice problems. 2 of these problems will have to do with energy conservation in springs, and the last problem will have to do with pendulum. So let's take a look at the information that we need to keep in mind for this unit. Essentially, this is just an application of energy conservation, right? That initial energy is equal to final energy. Energies in the oscillator will always be conserved, right? In the pendulum, we'll consider basically two moments, right? This initial moment when the pendulum is all the way down, and if we assume that this is a ground level, when the pendulum is all the way down, it only has which type of energy? Hopefully you said that it has kinetic energy, right? Let's think why, right? Does it have velocity? Yes, right? Because the bob is moving at some sort of velocity as it's passing through the lowest point. It doesn't have any height, so there's no potential energy, and there's no spring, right? So there's no spring energy. Let's consider this point then. So at this first point, there's the kinetic energy. At the final point, right, when you basically take the bob all the way to the left, then do you have velocity? Well, no, because the bob is momentarily stopped, so therefore there's no velocity, means no kinetic energy. Do you have height? Yes, therefore you have potential energy, right? So essentially, if initial energy is equal to final energy, and energy at this point is the potential energy, and energy at this point is only kinetic energy, then we have this energy conservation equation for the pendulum. So the kinetic energy gets essentially transferred to potential energy in the pendulum. Now, if we look at the spring, similar situation happens, right? At this point right here, the spring is all the way stretched. So it has the spring energy or the elastic potential energy, right? Again, it has no velocity and no height, right? So therefore no kinetic energy and no potential energy. And then this is the second point we're going to consider when it goes to the equilibrium position. So at equilibrium, delta x, or the stretch of the spring, is 0. Therefore, it has no elastic potential energy at this point, and it has just the kinetic energy. So for the spring, the energy conservation equation is kinetic energy equal to the spring energy, or as we call it, elastic potential energy. So in spring, this type of energy converts to another. In pendulum, it's potential into kinetic. Great. Now with this in mind, let's take a look at the first problem, at the first practice problem. So over here, don't be scared by the amount of words. It's not that hard. The 15 kilogram box slides on a horizontal frictionless surface with the initial velocity of 5 meters per second to the left. The box collides with and sticks to one end of a spring with negligible mass, while the other end of the spring is fixed to a wall. Due to this collision, the spring is compressed by a maximum distance of 0.75. So delta x is 0.75. Before the box starts oscillating. Determine the following: the magnitude of the work done by the spring force on the box during the compression. So work done, there's 2 equations for work, right? Force times distance times cosine of the angle between them, and change in energy. Well, we don't really know the force or the displacement, therefore it makes more sense to use this equation right here. All right. Now, for what is the work that is being done on this box, right? The box, let's just consider the box itself, right? So our system is the box without the spring. The box initial energy is the kinetic energy right here, right? Because it has velocity, it will have kinetic energy at the initial moment. But final energy, the box compresses the spring all the way and stops. Therefore, its final energy is 0. So work is equal to 0 minus the kinetic energy, or minus 1/2 mv squared, which is the formula for kinetic energy. So plugging everything in, 15 times 5 squared will give us 187.5 joules. That's the work done. Now, in the second part, we have to solve for the spring constant of the spring, right? Again, the energy conservation formula, essentially we have kinetic energy that is being converted, right, into spring energy or elastic potential energy. So the kinetic energy is 1/2 mv squared. Elastic energy is 1/2 k delta x squared. So this is where comes in the energy conservation that we learned on the previous page, right? If we rearrange this equation for k by dividing both sides by delta x squared and plug in all the quantities that we know, so delta x is 0.75 squared, we'll find that k is equal to the lucky number 666.67 newtons per meter. So that's our answer for the second part. Now for the third part, the maximum acceleration of the box during the motion. So what equation do you think about, right, when we're asking you for acceleration? Hopefully the second Newton's law comes to mind, right, that F net is equal to ma. Let's think about what is the net force here, right? The only force that the box is experiencing is the spring force, right? At least that's the force that will cause the acceleration. So therefore, the spring force is equal to ma. The formula for the spring force is k delta x. So we can rearrange this for acceleration and plug in for k delta x and m respectively. So our k was 666.67 from the previous part. Our delta x is 0.75. And our mass is 15. So the final answer for acceleration will be 33.33 meters per second squared. Fantastic. Now, let's take a look at another really quick spring example, and then for the last example, please keep watching because we're going to take a look at the pendulum. So this example, by the way, you can try on your own. Or if not, feel free to keep watching. So we have a physics student who secures a block with mass m to the bottom end of a vertical spring. The spring block system is designed to oscillate vertically if the block is initially released from rest at distance of delta x. Okay, so far we have m, we have delta x. Below the spring's natural equilibrium position. After conducting an experiment, the student records the oscillation period of the system as t. So we have the period of the oscillation. Based on these observations, derive an equation for the maximum elastic potential energy. Okay, so we need to find the energy, elastic potential energy. Sometimes it's also called elastic potential energy of the spring, right? So the energy, the formula for the elastic potential energy is this one, right? Well, we have delta x in this problem, what we don't have is k, but we're given mass and we have t. So what equation comes to mind? Equation, of course, for the period of the spring, which is 2 pi square root of mk. So essentially we just have to rearrange this equation for k, right, and plug this in here. Pretty easy, right? So divide both sides by 2 pi. Take a square of both sides to cancel out the square root. So then again, remember how we rearrange this, right? We distribute the square to each individual term. So t squared, 2 squared is 4, pi squared is equal to mk. Let me inverse both sides because I'm trying to rearrange for k. And then let me multiply both sides by mass. So I have k alone on this side. So all I have to do is just plug this in for k, right? And my question is done. So right here, instead of k, I have this expression in terms of variables that are given. So this is 1/2 times this times delta x squared as our final answer. All right, so finally we have a very important problem, right? Because we're going to find how this energy conservation applies to pendulums. So in this last problem for today, we have a simple pendulum that consists of a small bob of mass 0.5 kilogram. attached to the spring of length 2 meters. The pendulum is initially pulled back at an angle of 30 degrees from the vertical and then released from rest. Determine the maximum potential energy of the pendulum. So again, this is a very common problem. I've seen it on many tests. So I definitely advise that you keep watching this. So right here we have a pendulum. Right? Okay, perfect. So let's take a look. Here we have 30 degrees. So as we saw before, right, the conservation of energy for the pendulum, right, at this initial moment, right, the only energy is the kinetic energy, so 1/2 mv squared. And the final, at the final point right here, it's only the potential energy, mgh, right? So the thing is, right, we basically have all of these variables except the height, h. So that's what we really need to find, the height above the ground. And this probably maybe will be the most complicated part of this problem. So what we have here is the following. We have this length of the spring and this angle over here, right? And we also have this L. So what I want to find is the side over here, h, height above the lowest point of the pendulum. I want us to examine this triangle right here, right? I'll draw this here separately. Oh, this is supposed to be a right triangle. Okay. So bear with me. So this is L and this is 30, right? I want to find this side right here because if I find this side, right, I can find this side of this height right here essentially. So length L is 2 meters. So therefore, I can find this x, right? I have the adjacent side and I have the hypotenuse. So adjacent and hypotenuse, I'll use cosine. Cosine of 30 will be equal to this x over 2. Or if I multiply both sides, 2 cosine 30. Now, my height, therefore, right, we found this x right here. So we found this x. So as you can see, right, this x right here is the following. So h, the height, is going to be the total length of this spring minus this little height x that we found. You will have your height above the ground, right? Again, one more time. The whole thing is L. This part right here is x, and this whole, so we can find h by doing L minus x, right? Or L minus, let's see, I could have solved this in terms of L actually instead of 2. Let me put this in terms of letters, yeah? So minus x was L cosine 30 then. So this is our height. Perfect. So we can now calculate, right? We can now answer our first question, which is potential energy, mgh, right? Because we know that h is L minus L cosine 30. This geometry right here is really the hardest part of, I think, pendulum energy conservation. So if you got this part, the rest of the problem will be really easy. So mass is 0.5, g is 9.8, L is 2 times cosine of 30 degrees. We have energy as 1.31 joules. Great. So now let's take a look at the second part of this, which is finding the speed of the bob at the lowest point of its swing using energy conservation. So again, as we discussed before, right, the energy conservation for the pendulum is the following. Is the kinetic energy that turns into potential energy, right? We have to find velocity from this, so we can actually cancel out mass on both sides, multiply both sides by 2, and then take a square root of 2gh. Now remember, we have an equation for h, this one right here, so L minus L cosine 30. And if we plug in all of our numbers here, 2 times 9.8, L was 2, yeah, 2 minus 2 times cosine 30. We find our velocity as 2.3 meters per second. Great. Now we're almost done, guys. So number 3, right, we have to calculate the kinetic energy of the bob at the lowest point of its swing. But of course, the kinetic energy, right, this kinetic energy, it should be equal to this potential energy right here. So the third part, the kinetic energy, is equal to potential energy, which we have already found, 1.31 joules as our final answer. So just like this, we have learned, right, about energy conservation in pendulums. Great. So make sure that you try to work through some of these problems on your own if you have any doubts, and you can rewatch the videos, right, if you get stuck at any of these steps. Keep practicing, keep watching these videos. Thank you guys for watching. On your way to an A.